Thank you. Thank you. Thanks for the introduction. That was great. My name's Kevin. I used to work at Twilio, where I crushed it in 2011 and 2012, and again in 2014. I work at Shyp now. I also contribute to urllib3, which is the library that's underneath Python's requests. So I've done a fair amount of work with services and APIs and HTTP, and we're going to be talking about a lot of stuff to make your HTTP requests more reliable. So let's get started. So the talk title you might have seen it said chasing 5 nines. So what do people actually mean when they say that? You basically can fail like 0.001% of the time, right? That means if you have 100,000 requests, you want 99,999 of them to succeed, right? If you look at this like over a space of a year, that means you have about 5 minutes of downtime per year, right? That's what you mean when you say if my service is up, 5 nines worth of the time, like you're only going down for 5 minutes a year. And this doesn't tend to be like one failure out of 100,000. It tends to be like 20 failures in a row. So you can blow through this really, really quickly and leave yourself in a situation where you're saying, oh, well, I can't go down for the rest of the year, right, if I want to hit my budget, which is pretty tricky. So this might not be appropriate for your company, right? Like at Shyp, if we go down, like it's not great, but no one's going to chew us out over it, right? Like if you're Google or something, or if you're Twilio and you're down and you're dropping messages, you're looking at a lot of money, right? So for them, 5 nines is appropriate. For us, maybe not. And for your company, it might be appropriate, it might not. But picking the target means you have to invest certain amounts in your failover and in your procedures. And it might not be appropriate for your business and your team. So with that caveat, let's keep going. So with microservices, we basically take every single component of our architecture and we split it out into its own service with its own machines or running on the same machine. But one request might generate like a ton of other requests, right? So here's one request that's coming in. We're hitting a bunch of different stuff inside our service to do all kinds of different things. We've basically taken that one HTTP request and turned it into 8, right? And what happens is that means that a lot of different things can fail, right? So if we have 8 different services, that means there are 8 more opportunities for a network partition to take down our service, right? Or 8 different opportunities for any one of those requests to fail, right? 8 different opportunities for one of those services to be slow and increase the latency of our whole service, right? So you really need to think about when you're making requests back and forth, how reliable they are, right? And what am I going to do if this thing fails? And what am I going to do if this thing gets slow, right? So let's go through this. Just as a brief overhead, this is the sort of canonical interview question. And you really want to think about this if you're making HTTP requests is like, what actually happens, right, when I do this? Because then you sort of learn, right, at each point when it fails, you can reason about, well, is it safe to try something else, right? Is it safe to try again and that sort of thing? So the first step is your computer needs to turn google.com into an actual IP address of a machine somewhere in the world that I can send data to and get data back, right? So the way that does that is via a protocol called DNS. So I go and I ask my DNS resolver, I say, hey, google.com, can you tell me where it is? And it'll say, sure, it's at these IP addresses. And then you try the IP addresses, you send the data to it, you get data back. So that's the first step, right? If you're connecting directly to an IP address, you don't have to use DNS. But if you're connecting to like api.twilio.com or google.com, you're going to need DNS. Okay, so once I have an IP address, I need to establish a TCP connection. So I'm going to send a packet to the server. The server is going to send a packet back that says, okay, here's a port, and then we've got basically a connection set up where we can send data back and forth, right? So that's the next step. All these little subnotes here, if you type that in the terminal on your Unix or Linux system, you can read more about what that means in particular and how it fails, right? And the failure modes for it, useful reading you might want to take a look at. Okay, so now that I've established I can send data back and forth, I need to actually write the request to the server. So this is just going to be like get/HTTP 1.0 with whatever headers I want to send, possibly with the request body. that goes really fast, right? You usually write all the data, you break it into packets, you send it all, right? It's pretty fast sending it out. And then you wait around for the server to get back to you, right? So you send the request, you sit there, the server does some processing, and finally it's going to send you back a response, right? And then hopefully that response looks like valid HTTP, and if you're expecting JSON, hopefully it looks like JSON, and other stuff like that, right? So this is another important step that can also fail. So yeah, so that's what HTTP requests look like, sort of the cycle, and we're going to look at different parts of that and see where they can fail and how they can fail and how that'll bring down your service. Okay, so DNS, right? So DNS is what you use. You go to make requests and get data back. DNS goes down, right? You might think, oh, well, this thing never goes down, right? It's super reliable. It goes down a lot, actually, if you look through it. This was a week ago. Someone decided they didn't like something that was in the St. Louis Federal Reserve website. So they just fired a DDoS at enom, and it took down 33% of their websites, were just not resolving for something like in the neighborhood of a few hours, right? This was last year, Thanksgiving. CloudFront just went down. So if you're hosting things on CloudFront, it's like a static server, like an image and JavaScript server, like that just went down for about 100 minutes, right? It's just not resolving for 100 minutes. Probably the biggest one in recent memory was DNS Simple, which is a DNS provider. So they host your sort of DNS, and people like OpenDNS and Google Public DNS go and send requests to DNS Simple and say, hey, what are the IP addresses for the site? And then you tell them, right? This thing went down. That means if your name servers were DNS Simple, nothing was resolving for 11 hours, right? Like no one could reach your site for 11 hours. That's pretty bad, right? You know, like if we're talking about 5 nines, like yes, this might be rare, but 11 hours will blow through your availability for so long that it's a really bad situation to be in. So yeah, so worth thinking about and worth looking at. You know, this isn't going to bite you every day, but if it does, it's going to be really, really bad. Okay, so let's look at like actually what happens, like when this happens. If this happens, right? If something's not resolving or your resolver's down, or your name server's not returning any responses. So we make this request, right? This is the Python request library. Let's look at an example, right? So let's imagine that our DNS resolver is not resolving anything, right? So we're trying to make this request to api.acme.com, and whatever DNS resolver we've configured is not actually resolving any IP addresses, but we've set a timeout of 3 on the request, right? Anyone want to guess how long this will take, right? Like in that print line down at the bottom. 7 seconds? 27 seconds? 4 seconds? Okay, it'll actually take somewhere in the neighborhood of 2.5 minutes. Totally depends on whatever your system has configured for like the default DNS resolver timeout. Normally it's unset, which means it's just going to hang forever, right? This is just like the nature of DNS on most machines. It's just when things fail to resolve, it'll just keep trying forever and ever and ever and not ever give you a response back, right? So timeouts don't usually apply to DNS. It's a weird, rare thing. But we'll get more into it in a bit. So yeah, so when might this bite you, right? Let's say you use phones, and the phones use DNS to look up your API server, or you offer client libraries, and those client libraries use DNS to connect to your API server, or your own service uses DNS to connect to third-party services like Shyp or MailChimp or Twilio, and they're not resolving, right? They're going to be tying up resources for that 2 minutes, right? They're going to be tying up resources for that long period of time. And it can get you in really big trouble. Okay, so let's say your resolver goes down, right? Or just is resolving incorrectly. You might want to try using multiple different resolvers, right? So maybe you have Google Public DNS set up, that's the 8.8.8.8, and maybe you also have OpenDNS set up, right? So if one of them is hosed, the other one should hopefully be fine. Internally, some companies use DNS to resolve different services. I wouldn't necessarily recommend it. You might want to try just connecting directly to IP addresses and sharing those IP addresses around with something like Zookeeper or some sort of coordination service. The one place you can configure DNS timeouts is in etcresolve.conf, which is a file on your machine. You can set a shorter timeout there, right? So you could set a timeout like 5 seconds or 3 seconds, right? It's really too long, but it's better than 2 minutes to be sitting around. Finally, if nothing is resolving, you might want to just ignore the TTL, right? TTL is like it's a value that tells you how long this IP address is good for, right? So that I don't need to make a request every single time I want to read google.com. I make a request and it says google.com, here's an IP address, it'll be good for the next 5 minutes, right? But if everything's down and you're not getting a response, you might want to ignore that it's good for 5 minutes and just keep sending traffic to it, right? In the event of the DNS simple outage, right? If you're holding on to that last known good value, you're still going to be okay and you're still going to be able to make requests to it. If your provider goes down, right, the worst possible time for you to want to fix this is going to be like right when you're down, right? At least have some sort of plan in place for like, here's how I'm going to export my zone file, here's how I'm going to switch over my DNS. Just so you think about it, right? Maybe you don't have to do fire drills every 6 months, but at least it's good to think about like if this happens, here's our plan, right? Here's our plan for working around this. Okay, let's talk about timeouts. The basic idea of a timeout is really, really simple, right? When something is taking too long, you abandon it, right? And this happens in sort of all phases of life, right? If I want a book from the library and it takes too long, I might go buy it instead, right? If I'm in line at the store and I want to load, Twitter and it's taking too long, maybe I'll, check a different app or something like that, right? The key point is your users have a timeout whether your system's configured one or not, right? So like if I'm trying to sign up for a service and it's too slow, or if I'm trying to buy something and the site's too slow, then I'm going to time out and use something else, right? So there is an upper bound on like how long your users are willing to wait for something. Your service should fit within that, right? If your service doesn't fit that, your users are still going to time out, right? Even if your service is not, right? So might as well set an upper limit on how long you're going to take to respond to a request, right? Because it's better to return anything, or do some kind of failure fallback pattern, right? Than it is to just wait around forever and never get a response. Okay, so you want to kind of configure timeouts outside in, right? So let's say your users are talking to server A. Server A talks to server B. Service B talks to service C, right, and all the way down, right? If service A is a timeout of 30 seconds and the service that it talks to is a timeout of 35 seconds, service A is going to time out before it, right? So if you control both of those servers, right? Like let's say I control an API server and an auth server, right? And the API server's going in and talking to that auth server. The auth server better have a shorter timeout than the API server, right? If I make a request for auth and just waiting around forever, then that's going to lead to really bad things, right? So as you go deeper and deeper in your stack, you want to have shorter and shorter timeout set. It's just that way, right? Whatever the lower bound is of things that you're sort of talking to, right? If I'm an auth service and I'm serving requests from 5 different services, whatever the lower bound is on those people's acceptable response time, that's my acceptable response time, right, for the request. Another thing you want to think about for timeouts is how long can my service afford to spend processing requests? So when you're processing a request, you're using up resources in your system, right? You're using up file descriptors, you're using CPU, you're using memory, you might be using disk space, and those are all expensive, right? If requests keep coming in, and you're not dispatching them and closing the resources, right? You're eventually going to run out of space on the machine, right? So another reason to set timeouts is because you might not be able to afford to wait around and get really slow and consume a bunch of resources, right? Let's say we've determined our service can handle 100 requests at a time, right? Maybe our database can handle 100 connections, right? And in normal conditions, each request takes 1 second, and we have 20 requests per second. Right, so in normal times, we have 80 spare workers, at any given time. Now, all of a sudden, let's say a downstream server gets slow, right? Our auth server or our fraud server or the database server or whatever we want And suddenly talking to that service is taking 6 seconds per request, right? Now we have 20 workers handling each request. Each request takes 6 seconds, so we need 120 workers. We're now oversubscribed by 20 workers, right? If we set a timeout at our sort of maximum value, right? If we set a timeout at 5 seconds, sure, maybe we wouldn't be responding to any requests, but at least that downstream server being slow wouldn't affect the servers upstream of us, right? So a timeout's a way that you can sort of conserve resources, right, and make sure that you're not spending too much time on any one resource. Sort of related principle is you want to fail early if you can't serve, right? So if that downstream service is being slow, right, let's say it's got like, a thread pool database connections the same way, and that pool is full, then don't wait around forever trying to respond to, don't block trying to wait for available connection, right? Don't get really, really slow just waiting for things to get better. Just fail early, right? If you can't get to the request, just fail as soon as you can. As soon as you know that you're not going to be able to do it, that's a good way to keep things at least from getting really slow, right? And at least keep error conditions from propagating through your service from service to service. Okay, socket timeouts are liars. So the default approach of HTTP requests is you set a timeout on the socket, right? So when we established that TCP connection, we opened a socket on our machine. And normally when we set timeouts, we set a timeout on that socket. And what that tells the operating system is, okay, if the timeout is 5 seconds, if we haven't seen any data coming, either going out or coming in for 5 seconds, then like raise an error condition, right? And throw an error on the socket. This is a liar in the sense that it doesn't accurately reflect wall clock time a lot of the time, right? This is the sort of default timeout setting that you get in most HTTP clients, and it doesn't reflect wall clock time at all. So here's an example. This is the shortest possible HTTP response I can send, and I've set up the server basically to send 1 byte every 29 seconds. So if my timeout, if I've configured that timeout to be 30 seconds, I will never actually hit the timeout, right? This request will take 13 minutes to complete, but I'm never going to hit that timeout because I'm always going to send 1 byte and just refresh that timer every time for 13 minutes, right? So this can lead to a scenario where you're like, oh, okay, well, nothing will take longer than 30 seconds, so I'll be okay. And instead, you're waiting on this response for 13 minutes, right? So in that sense, you need to be careful about how long things are actually taking, right? And whether that's a desirable property in your system or not. Another way socket timeouts are liars. So let's say we're trying to make a request and the remote box is down, right? Like Amazon killed it, or it's just not listening. So for example, the way I like triggering this is by connecting to port 81. So we're going to send requests to this server. Again, we're using Python requests just for fun. And we've set a timeout of 3 on this request again, right? Anyone want to guess how long this will take? Like in terms of wall clock time. All right. It'll actually take 18 seconds. And the reason is google.com has 6 different addresses. I guess 5 different addresses. And each one will try that for 3 seconds, right? It'll try each of those for 3 seconds. This is just another thing that'll like get you. And you need to check how your client actually behaves in these scenarios. If it tries a connection and fails, how will it behave, right? Will it try another IP address or will it just fail, right? Like curl, if you try the same thing, it'll actually take 3 seconds. So you need to really know how your client behaves in situations like this. Another one where this can catch you up is HA proxy. So by default, HA proxy will retry failed connections 3 times. So I might think I'm setting a connection of 3 seconds, a connection timeout of 3 seconds, and behind the scenes, HA proxy is actually retrying that connection 3 times before it fails. So you need to keep an eye out for these and sort of understand how your system behaves and understand how your clients are behaving in all sorts of failure scenarios. If you set one timeout value, it's set on both the connection attempt and on the read. This may or may not be desirable for your situation. For example, connections usually take about 100 milliseconds or less, right? And if I've said, okay, it's okay for this thing to hang out for 30 seconds, right? If it's okay for the server to process things for 30 seconds, you're going to be waiting around for 30 seconds for that connection to fail, right? When you know it's probably either going to succeed or fail right away. So one thing you can do is set separate connect and read timeouts, right? Here's an example of how you can do this with requests. Again, you're going to want to look at the HTTP client you're using and how it actually sets timeout values, right? But yeah, usually setting these separately is a good idea. It's good for reliability because you want to fail faster if you know the connection's not going to succeed. Okay, so timeouts, right? So things are timing out or failing or getting slow. You want to set timeouts. For everything that talks to a third party or everything that talks to HTTP in your system, you want to say what's the maximum amount of time that we can wait around for this thing to succeed or fail, right? And if it fails, what do we want to do in case it fails, right? Like what's our fallback, right? If you're Netflix, right, and you're trying to fetch someone's available movies, it might be the fallback is just let's show just a bunch of popular movies, right? And you want to think about what's an appropriate fallback in all these cases, right? If it's your auth server, you can't just fall back and say, oh, well, this person's okay or this person's not okay. Again, know how your HTTP client behaves, right? In all these sort of scenarios, know what it's going to do if it can't succeed or not. Another thing you can do is just set a wall clock timeout, right? So run a request in a thread, measure the amount of time it takes. If it's taking too long, then close the connection or stop reading the request, and then implement your fallback. So if you're looking at Go, for example, the response header timeout in Go is entirely just based on the amount of wall clock time, right? Like they don't even bother with socket timeouts. They just say, well, if it's taking too long, let's close the connection and report that we failed, right? And I think you'll see more of this as we sort of go forward, this wall clock-based timeout system versus socket-based timeouts. So how do we find this, right? You have to measure, right? You have to measure the latency of your system. Definitely for every sort of HTTP request that you're making, you want to measure how long it's taking. And get sort of the percentiles, right? Like what's the median amount of time this is taking? What's a 90th percentile? What's a 95th percentile? What's a 99th percentile? So this is from our stack at Shyp. We go and we make requests to Google Maps for all kinds of data. And you can see here we had a big spike in latency, right? Fortunately, it was manageable, still under a second, which is fine for us. But yeah, if that's got to 15 or 20 seconds, that's something we definitely want to know about, right? And implement our fallback, which is just computing distances by the crow flies distance to the place that we're trying to go. Okay, let's talk about retries. So retries are another really, really good stability pattern for your service. Again, pretty simple. Just if a request fails, retry it, right? Unfortunately, I just said it was simple, and now it's actually, I'll explain why it's complicated and how you can deal with it. But let's go through and do that. When a retry is good, so temporal failures. Let's say a service goes down or there's a network partition and the partition makes things unavailable in your service, right? Makes it hard for one box to talk to another box for 5 seconds, right? Well, if we sleep for 6 seconds and we try the request again, it's going to succeed, right? So you'll see this a lot. You'll see boxes, go down or close the socket briefly to restart HAProxy or restart any kind of service. And you'll see some temporal failures there, right? But if you sleep and try again, then it'll succeed. Single component failures. So let's say we have 3 hosts, and one of them is a folder that's on fire, and the other 2 are good. And we make our first request to the on fire server, and it fails, right? Well, maybe if we try that request again, we'll get a different box, right? If we're round robining requests between all our boxes. If we try again, then maybe we'll get a box that's not on fire, and we'll succeed, right? So this is a really, really useful pattern that you can implement for request fails, try again, right? The tricky part, one of the tricky parts of retries is if a server is down or is slow, and you're retrying those requests, you're going to be multiplying the amount of traffic that's going to that service, right? When it's already down and already hurting, you're going to be multiplying the amount of traffic that's going to it, right? So normally, what people recommend is you want to have some kind of exponential backoff, right? So the first time a request fails, sleep for 1 second. The next time, double it. The next time, double it and sleep for that amount of time, right? That way, as more and more requests are coming into the system, at least every client is taking a longer amount of time before trying again. It's good too, instead of making this number exact, like jitter it by a little bit, right? Let's say, for example, you have a whole bunch of people that ping your service exactly at 12 noon, right? 12 noon, they're going to send out some kind of reminder message, right? So all of those things try at 12 noon. They all get a failure response. They all sleep for 1 second. They all try again. They all sleep for 2 seconds. They all try again, right? It's not great. You just end up repeating the traffic patterns over and over again, right? So some amount of jitter is good. You just increment a random variable and sleep for 1.01 seconds or 0.99 seconds. You just jitter it a little bit, right, to just get off those offsets. And that can be really useful too. Okay, when can you retry, right? It would be great if we could retry everything, right? If we make a request and it fails, try it again, right? That would be great. Unfortunately, it's a little bit more complicated. There's a notion of idempotent, right? And what this means is idempotence is a really nice property for our servers and our requests to have. It basically means if I make this request multiple times, the end state of the world will be the same as if I made it one time, right? It's a very nice property because that means like if the end state of the world is going to be the same whether I do this one time or 1,000 times, it means I can just retry I can just retry as many times as I want if things fail, right? So let's talk about this, right? So idempotent actions, right? So here's some things that are idempotent. If I go and retrieve like a profile from Facebook or Twitter or whatever, if I make a GET request to go get that profile and it fails, I can always just try it again, right? At the end of the day, I'll have the profile, right? I can try it 1 time or 1,000 times. I'll just end up with a profile, right? I can't like modify the profile somehow by retrieving it, right? Setting a user's email, right? If I try this once, I tried 1,000 times. At the end of the day, the email's just always going to be foo@bar.com, right? Doesn't matter whether I do it once or 1,000 times. The nice property there is if I fail, I can try it again, right? Emptying a bank account, right? If I try this 1,000 times, the balance of the bank account is going to be 0 at the end of the day, right? So yeah, so the nice property there is you can always retry it. If the server succeeded but indicated that a failure to the client, we can just try it again, right? If the bank account emptying failed for whatever reason, I can just go try it again. Things that are not idempotent, sending an email, right? Let's say I try to send an email and that fails and I try it again. Suddenly you might end up with 1 email in someone's inbox, you might end up with 2 emails, you might end up with 1,000 emails. You don't know, right? Charging a credit card, right? If I charge someone's credit card and I get an indication of failure and I charge a credit card again, that users might get double charged, they might get charged once. It's not clear, right? So you need to be really, really careful with these sorts of things that you're not doing this twice, right? This is the sort of situation where retry can be really harmful, right? And unfortunately, these tend to be the actions where we want to have the most reliability in our HTTP requests. They tend to be around these not idempotent actions, right? Like sending SMS messages for Twilio is a really, really, really important thing. We want to make sure that sending exactly 1 SMS message, but it's not an idempotent action, right? Okay, so when can you retry, right? So for non-idempotent requests, you can retry if the data never made it to the server, right? So if we tried to establish a TCP connection and we failed, we can always retry that request. We never sent any data to the server, right? You can't say the same. Let's say we tried to write data to the socket. If we wrote data to the socket and then got an error, we couldn't retry, right? Because the server might have started processing that request. It might have started figuring out what's going on, right? If we wrote all the data and we're waiting around for the server to respond, we can't try again because the server started processing it. It might have charged a card. It might have sent that message. You can't try it again. This is really, really hard. Usually you have to read through the source of your HTTP client to see what's going on. You definitely want to be aware of the sort of errors that can be raised on a socket. and when in the HTTP request lifecycle those errors came up, right? Hopefully your client has sort of good errors. It lets you distinguish these things, but not in all cases. If you get a response back and it's a 429 or a 503, usually that means you can retry, right? A 429 means you're sending too many requests, which is bad in a sense because you're sending too many things, but it's also good because it means it didn't process the request. You can try it again, right? You need to sleep for a little bit of time, but at least you have the certainty about it didn't do any work, right? It didn't do any processing. Same with a 503. Really need to know about the semantics of your server, but if you've configured it correctly, a 503 just means, well, like the thread pool was unavailable or the database pool is unavailable, and I didn't actually process this request, right? That's also a good piece of information to know. Yes, your server's having trouble, but it also means we can try it again, and we know that the request didn't get processed. OK, so idempotence is good. Not idempotence is not good. How can I make things more idempotent, right? If everything was idempotent, it would be great. It would be a much better situation. We could retry indefinitely when we got a network partition or other kind of failure. So let's look at two API examples. Let's say we have an emails API, and we send this email. So we send an email by posting to the emails endpoint, right? And we send some data. We say we have a to address, we have a from address, and we have a body of the message. The problem is here with this sort of API, if I send it and it fails, I don't know whether it's safe to keep going, right? Oops, I'm way over time. Instead, if I did a put API, right? If I generated a message ID and then sent this request and it failed, I could try it again, right? And hopefully the server would have some sort of consistency check that said, oh, we've already sent this message and we can't send it again. That's about it. The last thing I want to say is just know your client, right? Know your server. Know how they behave. Know how they throw errors. Know what that error means about what went on with the request. I have a tool called Hams, which you can look at. Hams is a sort of malicious HTTP server. It'll send back a whole bunch of error conditions. And you can use this to test out your clients in different failure scenarios and see how they actually behave. That's it. Thanks very much for listening, and I'll be happy to answer any questions over on the side after the talk.